Good morning, good afternoon, good evening, everybody. My name is Kartik. I'm one of the co-founders of ETH Global, and I'm super excited to welcome all of you to ETHOnline and our Verifiable Compute Summit. All of you are watching this on ethglobal.tv. This is a live interactive platform, so if you have any questions or comments or anything that you type in the chat, we get to see it and respond back to you. So as you see a lot of our talks today, feel free to ask any questions and we get to answer them for you and address them live. This is the first week of ETHOnline, and if you're joining us for the first time, ETH Global is an organization with a very simple mission. Our goal is to onboard thousands of developers into the Web3 ecosystem. We do this by running hackathons and summits, both in person and async, and this has been already our second biggest hackathon ever. We have over close to 1,600 hackers from 89 different countries, spanning 26 time zones, participating across the world. And we got 10 more days to go before project submissions are due. But today is about our second summit for this hackathon. And we're going to be talking about everything verifiable computing related. We have an awesome agenda for you today. We got 5 talks that are going to cover, 6 talks. We're going to cover all interesting things that you need to know about what's happening in this space. Our first talk of the day is going to be from Zach. And we're going to talk about how we can verify Web3 and Web2 and Web3 data and merge that to just make computing on-chain more easier. Then Yusha's going to talk about ZK email and how you can actually use those primitives to bridge more information on-chain. Mihal is going to talk about Snark miniaturization and how that field is improving from kind of the Nethermind team. Remy is going to talk about more on-chain FHE applications and improvements there. And then Eunice is going to cover all the things about privacy and scalability that the MENA team is doing. And our last talk of the day is going to be from Baz, and we're going to talk about how do we actually build more tools to help scale more conspiracies. It's going to be a very interesting talk of the day. That's the official agenda. And anytime you have any questions, just feel free to ask them in the chat, and we will be able to address those questions directly and relay them to our speakers. So without further ado, let's get started with our very first talk. And for this, I'd like to invite Zach from Aztec to talk about merging Web2 and Web3 with verifiable compute. Welcome, Zach.
Hello. Can everybody see my screen? Kartik, is everything showing there? Hey, awesome. So, hello, everybody. My name is Zach. I am the CEO and co-founder of Aztec Labs. Aztec is a privacy-focused layer 2 for Ethereum. The goal of Aztec is to enable the fully on-chain smart contract ecosystem that Ethereum has, but one where you have private state. This, in our opinion, unlocks a lot of things that will dovetail with what I'm talking about today. So what's the talk? What's going on? I want to go through three things here. One of them is, what is the actual value of Web3? Let's remind ourselves of why we're here, what's good about this, and what are some of the challenges with making it mainstream, and how does this dovetail in with connecting with Web2? And how can this predict the future paths that Web3 can take? So what are the core value propositions of Web3? You know, you have the famous 3 properties of permissionlessness, composability, and trustlessness. It's a rather core tenet of blockchains that anyone can participate. Anybody can transfer the network. There's no central authority telling you whether you can or cannot send a transaction. You have composability, and this is the core property. This is why networks like Ethereum became so popular. The idea here is that anybody can deploy smart contracts, anybody can interact with a smart contract, and if you have a dApp or a contract that's deployed to Ethereum, anybody else can turn up and use it in their own smart contracts. So if somebody builds a token standard, great, other people can use that token standard. If somebody builds a decentralized exchange, great, I can build an application that uses that as a component. And you have trustlessness. You don't rely on third parties where you have conflicted interests. For example, Web2 is saturated with these kinds of services where you are being led to believe that you are the customer, but you're really the product, and the customer are advertising agencies or data miners or data brokers. So Web3 really provides a vision of a very different world to Web2, where everything is permissioned. You have anti-competitive barriers to entry, you have walled gardens, you have moats, everything, and organizations benefit greatly from vertical integration, where you extract efficiency by controlling the entire tech stack and not letting anybody interoperate with it. We're seeing some of this in the West, but in places, in other countries, you end up with complete monolithic do everything apps, which really takes us to the extreme. And so Web3 can bring a lot of value to the world. It can bring a lot of value to Web2. But we have some problems. So we have some serious adoption challenges. There's obviously scalability. Then you also have what I've got here on the left-hand side, they're more adoption challenges, not core protocol challenges. So you have issues where, how do you do access control? If you want to interact with a regulated space, for example, or you just want to determine whether somebody is a stakeholder in your protocol. If you want to create a DAO where you have governance, right now, you only really have two options. You have autocracy, which is the rule of one person or a multi-signature, or you have plutocracy, which is the rule of people who have tokens, where the tokens are tied to economic incentives. Both of these modes of governance are terrible. There's a reason why nobody is raving, at least in the West, about autocracy and plutocracy. If you can identify stakeholders more effectively, then you can have better governance mechanics. Identity management. Who the hell are you? This doesn't matter when you're trading meme coins. It really matters if you want to hold a real world asset, or if you want to perform real world payments, or if you want to connect what you're doing in Web3 with some kind of account on Web2, like a Google account or an Apple account. We have problems with ecosystem fragmentation, where in order to solve scalability, we have a proliferation of layer 2s, where bridging between them is very complicated. The UX is very painful. And then on top of this, you have this overarching issue of privacy. Everything in Web3 is transparent. Everything can be surveilled. Nothing is secret. And the more and more Web3 breaks into the mainstream, the more this is going to become a serious problem. So that's the lay of the land for Web3. So why am I talking about Web2, right? Like, where the original blockchain cypherpunks, they didn't like Web2. They were like, Web2 sucks. We're going to make a new web. We're going to increment the version number. So I think that ignoring Web2 is problematic. I think this is generally the way the industry is trending over the last few years. What happens in Web3 and crypto is kind of more and more becoming its own, like, strange little island of cyberspace that is inaccessible to other people, to other entities working at different networking layers. And I think this is a problem. I think there are three fundamental theses around why Web3 is valuable that all require interoperability, strong interoperability with Web2. This idea of an enhanced Web2, but also the basic thesis of using Web3 as money or as a coordination engine, using things like decentralized autonomous organizations. So why care about Web2? Really, because you can connect what happens off-chain with what happens on-chain. It's that simple, really. It's just that's the meat of it. Like, being able to trustlessly, or mostly trustlessly, bring information from Web2 into Web3. That's really important. So these are some of the on the right are some of the protocols that kind of are widely used as infrastructure in Web2. You have the JavaScript JSON Web Tokens, Apple Touch ID. You have the WebAuth format. You have TLS signatures, which are generated and signed every single time you visit a website. And the FIDO Alliance handles standards widely used in Web2, things like handling passkeys, message authentication, stuff like that. And open banking is something that is being trialed in my home country, which is an API that allows websites to interact with a consortium of banks to do basic payments, transfers, things like that. It's basically like a really crappy version of Web3, but you get to talk to banks. So if we can validate these technologies in Web3 in smart contract contexts, this allows us to say, basically, to prove something happened in Web2. Like, I interacted with a website, I received an email, I own a certain Google account, and that basic information is extremely important. It means that you can solve, for example, the user experience problem with Web3. Imagine if, instead of having a public and a private key, you signed in with Google. I mean, that would be, for most people, unless you're holding an enormous amount of money, that's a perfectly fine user experience. So it allows you to bring Web 2 user experiences into Web 3. It allows Web 3 benefits to be migrated into Web 2 applications. If you need a trustless ledger, if you need records of ownership that are portable, if you want to interact with just with portable standards, portable identity standards, like Web 3 is the best home for those. And right now, Web 2 applications have no ability to interact with this kind of thing. So I want to give a taste of what's to come. So is this going to work? Is it playing? Is it not playing? It's playing. Okay. So this is, what is this? So this was one of the folks at Aztec, Pedro. He is creating an Aztec transaction by through his Apple Watch. Basically, the transaction data is sent to the Apple Watch. The Apple Watch is generating a signature using Touch ID, and that signature is being verified inside a smart contract. So just a taste of what's to come, but that was basically signing into a Web3 account using an Apple Watch. That doesn't hold any particular Web3 specific secrets. So the interoperability layer between Web2 and Web3, it's all about verifiable computation. It needs ZK cryptography, and I mean real ZK, none of this fake ZK VM scaling stuff. I mean privacy. I mean cryptographic proving systems that use the zero knowledge property of a ZK snark. Basically, prove this old school weird ass Web2 protocol is valid. And this protocol contains sensitive user data, it contains session keys, secret keys, passwords, all sorts of junk you do not want to leak outside your device. Which means that your proofs that you're generating, proving I received an email from somebody, or proving I possess a passport from a certain nationality, or I'm interacting via the TLS protocol with a certain website. Proving all of that information has to happen. If you do not want intermediaries, and you want to preserve the trustless nature of Web3, that needs to happen client side. And that comes with some interesting trade-offs. So this is what I'm calling real ZK. I'm absolutely grinding an axe here because the ZK tag has been very much adopted by anyone using succinct cryptography or verifiable computation, such as the way of the world. But for the kind of stuff I'm talking about, it's a very different environment to most ZK outfits, because if you're proving stuff client-side, you have massive constraints on what you can do. You have limited memory, you have limited storage, your hardware is like potato hardware. It's a laptop, it's a phone. If you're interacting with a DApp, that's going to be, or a web app, that's going to be in a web browser, which means your prover has to run in WebAssembly, which is very slow compared to, if you're proving a ZK VM, you have access to a lot of additional resources in a centralized context that this kind of technology that I'm talking about doesn't have, which presents some unique design challenges. So the reason why we haven't seen yet a massive proliferation of verifiable computer Web3 is because it's hard, basically. I've been in Web3 for 7 years. I've been working on ZK Snark's cryptography verifiable compute for 6 years. And the state of the art has changed a lot over that time. From back in the day when I started, it was a big deal to be able to prove the pre-image of a SHA-hash. And like nowadays, where the complexity has grown by multiple orders of magnitude, and the industry has collectively massively pushed the state of the art. I like to think myself and Aztec has played a significant role in this. But to give some examples of things that are challenging to do, if you want to do Touch ID, you might want to verify an RSA signature, or a SecP256R1 elliptic co-signature, which is not the Ethereum curve. These things are hard to do. It requires lots of big integer arithmetics, not to do in a snark. But then if you want to get into the meat and potatoes of old school Web2 protocols, like say you want to verify a JSON web token, or you want to do an Apple Touch ID signature, you're going to have to do weird things like interpreting JSON, JavaScript object notation inside a ZK snark, where you're going to have to parse this JSON string, which is going to be variable length, variable number of fields, possibly an undefined JSON schema. And you're going to have to handle this all in a snark in a circuit that's being proved in potato hardware client side. You have to pass regular expressions, which is heavily used in ZK-email, which I believe are talking after me, so I won't go too much into the details there. And anyone who's actually dived into Web2 cryptography will know the standards are messy. So FIDO2 is the there's a messaging format for like how to sign Touch ID, do passkey stuff, and it's a horror show. But this is the challenge that we have to overcome if we want to bridge Web 2 and Web 3. And within the next by the end of this year, these are all going to be solved problems if they aren't already, and very accessible problems through languages like Noir, which I might talk about later. So going back to the theses around the use cases, right? Web 3 is Web 2++. Basically, provide the same kind of services as Web 2, but just do it better. Focus on efficiency and open participation to lower barriers to entry, using composability as a strength to trade off against the existing world of Web 2, where you use vertical integration and walled gardens. You do complete opposite. We're already seeing things like this with decentralized social media, with composable identity protocols like ZK passports, where basically you can contest the benefits of vertical integration by effectively crowdsourcing, making it so that you're aligning incentives so that you have a large number of different application developers that are going to benefit from interoperating with your protocols, with your applications, and thereby enhancing the ecosystem as a whole. This is blockchain's killer strength that needs to be leveraged if Web 3 is going to compete with Web 2. Other examples are things like just open micropayment networks. Just if you could do, just a basic payment system for the internet that you can integrate into any web browser that can do micropayments without tapping the Visa or MasterCard and their high fees. That would be revolutionary. And what I'm calling Frankenfry, basically a hybrid between TradFi and DeFi. So it's not completely decentralized because, if you want to do something in the real world with the US or the UK, you probably have to follow a couple of laws. But maximizing just how accessible and permissionless this stuff is by using as much of Web3 technologies as you can get away with. Web3 is money, the fundamental thesis, right? Why is this valuable? Why was Bitcoin created? But digital tokens it's just the first step. Web3, the real potential of Web3 is to create a global issuance and settlements layer for the world's assets, every single asset. If you can digitize assets around the world and put them on a single programmable ledger, what that enables is massive hyper-fungibility of assets, because stuff that is illiquid, that can't be traded because the information about it is hard to find, and and there's some front desk somewhere that has office hours from 1 to 3 p.m. All of that goes away, and you end up with effectively hypervelocity of money, because you end up in a world where the assets on your global ledger start to look a lot like money, and this crosses down the barrier to entry for providing financial services. This is the whole banking the unbanked thesis, or contesting large centralized banks using Web3 technologies. This has not been successful remotely up until today. And I would argue the main reason for this is the lack of strong identity solutions and privacy guarantees on Web3. And that's going to change. And then you have Web3 as a coordination engine, basically the DAO thesis. How do you organize people to work towards collective goals? I do think this is, despite the infancy of DAOs and their governance problems, this is extremely powerful as a basic primitive, because enabling effective peer-to-peer coordination and communication is extremely hard. And I think Web3 does it better than anyone else. Nobody does it well. But here's some predictions we're going to make for the future about how this is going to develop. I think that decentralized organizations will eventually be granted the status of legal persons in most Western countries. What is a legal person? So in the United Kingdom, which is a legal system I'm more familiar with, there are two kinds of legal persons. There is human beings, and there are limited liability corporations. And a legal person can sign a contract, they can own property, they can be held liable for that action. So a legal person can sue somebody, they can be sued. If we can create a world where a decentralized organization has access to these protections, to these privileges and responsibilities, then you can meaningfully have DAOs that own assets in the real world, which interact with the real world, that can be held accountable for their actions in the real world, and affect the real world in a much more real way than existing DAOs. Obviously, this is a very far out prediction, because the quality of governance needs to improve dramatically. But again, I would argue privacy technologies and verifiable compute are essential for this, because for high quality governance, DAOs need to identify who the hell is a stakeholder in the protocol, like who should be given governance votes. And right now you can't do that. I can't like permissionlessly in the DAO say, well, listen, I made a bunch of pull requests into your project on GitHub, and here's the bloody ZK proof about it, like, and this is my GitHub account, and I can link this to an Ethereum account in a Sybil resistant way. Therefore, I'm a stakeholder in your protocol. So give me some governance tokens. You can't do that right now, but within a few months, you will be able to do this. I think that decentralized organizations are going to thrive as goal-driven organizations. This is something that companies are terribly bad at. If you in this world, if you want to get something done, if you want to get shit done, and you need the effort and attention of many hands and many minds, a company is really the only way you can do that effectively, I would argue, unless you're a government. But companies have their own problems because they have stakeholders and shareholders that are responsible for. If you build a company to do a thing, and then you do the thing, for example, say Google. Google's main mandate originally was search sucks, we're going to solve search. But then you solve search, great. What now? Well, the company doesn't die, right? Because the company has shareholders that like making money, and so they find ways for the company to persist and become almost what I would call a zombie corporation. And I think this is how you end up with entities like Fang, who spend enormous amounts of money on dead-end projects and are like deliberately anti-competitive. They explicitly hire talent out of the market so competitors can't access it. They buy startups to kill the ideas and protect against competition. As a thought experiment, would the world be better off if Google just did search and nothing else? I think that DAOs are very good at that kind of goal-driven development where you want to do a thing, you find like-minded people, you make a DAO, you do the thing, and then you will go your separate ways and you walk off to the sunset. And maybe the DAO persists, but it persists with a rump mandate, a reduced mandate, just to manage and govern the thing that you created. It doesn't have an existential need or desire to continue to grow, to seek to seek further profits and further markets. It just, you do the thing, and then you move on with your life. Anyway, that's my view of how DAOs will succeed. So when it comes to getting things done, I think that there's a spectrum. I mentioned before, if you want to do something interesting in this world, you need to do it via a company. Well, there's also charities and NGOs, but they occupy two ends of a spectrum, where on the charity side, your organization is very values driven, but it's very hard to align incentives because you have no bottom line that you can measure against, and they are very intensely difficult to coordinate. Charities are legendary for being ineffective at using their funds and fulfilling their mandate. In the worst cases, charities are incentivized to not solve the problems that they're supposed to be solving, because then the charity will not have a reason to exist anymore. And companies have the opposite problem where, okay, great, you have strong incentives because people want to make money, but the values of the organization are very much subordinate to shareholder returns. And this cannot be escaped. And so I think there's something missing in the middle, where you can have an organization that does have some kind of profit incentive to ensure that you have alignment and you can keep the wheels on the bus, but you can still preserve the values of an organization, and have values at the forefront of what you're doing. This is just more of a hypothesis than a firm statement of fact. I think that decentralized organizations are going to fill the gap in that spectrum, and it's going to create a very interesting world. Right. Okay. So I'm running a bit out of time. I think I've got a couple of minutes left. So I want to talk a little bit about just the future of Web3. Where are we going? What will the world look like if we can bridge the divide between Web2 and Web3? What will the world look like if we don't? So I think there are three paths ahead of us. We have the sad path, the bad path, and what I'm calling the wild path. So let's start with the sad path. The sad path is basically we can't solve the fundamental infrastructure problems in Web3. We can't solve scalability. We can't solve privacy. Basically, imagine a world where what you can do with Web3 in 5 years' time, in 10 years' time, is no different to what you can do today. I think that the infrastructure bottlenecks will mean that Web3 cannot be competitive with Web2. It cannot scale beyond synthetic tokens and meme coins, and it's a useful store of value, digital gold, but it's not an innovation layer. Womp womp. Everyone pivots into AI or something, and Web3 is just remembered as that weird phase that society went through in the early 21st century. The bad path is we solve the scaling issues, but we don't solve the privacy issues. We don't utilize verifiable compute to its maximum. I would argue that what this does is Web3 creates the infrastructure for a global transaction and settlements layer, but the need for privacy forces applications into off-chain trusted spheres. Basically, like the trustlessness, the decentralization of Web3 becomes a Potemkin village. Basically, it's just for show. It's not real. And worse than that, centralized banks co-opt Web3. Authoritarian governments, state bureaucracies co-opt Web3. They use the technologies that we've developed to create decentralized ledgers, to force financial transactions within their jurisdiction to settle through these ledgers that they can view, and basically creates a warrants financial surveillance regime. This is basically creating a surveillance state. Yeah, I think this is where we're trending right now. If we don't solve critical problems with privacy and verifiable compute. And the wild path is if we do solve them. This is what Aztec's trying to do. And I think what a lot of people attending this conference want to do. Basically, I think that if we can create strong privacy guarantees, if we can create blockchain networks that have verifiable compute, they have private state, you have private identity, it doesn't stop the bad path playing out, because ultimately, open, transparent ledgers are a wet dream for a bureaucratic petty despot or a tyrant, and they're going to try to use this stuff. It's only a matter of time until someone like a Cambridge Analytica takes this technology, wraps it up in a bow, and starts selling it to people with bad intentions. But at least there's a way out. There's an alternative path if we can get this to work. If you have strong identity guarantees, you have this flourishing of hybrid Web2, Web3 applications. You have off-chain assets that can be put on chain. You have monetization models where data stays with the user. The user is the customer. The user is not the product anymore. And the efficiencies and composability can contest efficiencies from centralization. So at least you have a world where you have decentralized organizations existing, contesting like centralized organizations with conflicted interests. Users have a choice with the kind of services they use in a way that they don't now. Right now, if you want to interact with the modern world, you must subordinate yourself to predatory business practices that will harvest your data, analyze your actions and your patterns through AI, and use the output of those algorithms to manipulate you, either to maximize profit returns or something altogether more sinister. And I do think that Web3 will provide an alternative to this if we can solve the privacy problem. And then it's on us to ensure that the user experience and the developer experience is strong enough that this path wins out. Right, I'm just going to end with a couple of final thoughts. I've styled this section final thoughts. I'm going to be honest, this is a shilling section. I'm the CEO of a company. I'm going to shill now. So if you want to, I've been trying to pull privacy technology into the world for 6 years now. And the forefront of these efforts is the Aztec network and the language that powers it, Noir. Noir is an open source zero-knowledge programming language. It is completely agnostic to the cryptography and zk-SNARK program, technology underneath it. So, its use cases are much wider than just Aztec specifically. And if you want to tinker around with verifiable computation, this is the place to go. Go to noirlang.org. We've got plenty of examples, ways of doing crazy stuff. We're working on things like zk email, WebAuth, basically a Touch ID. If you want to do something weird and funky that involves authentication or cool algorithms with verifiable compute, you'll find it in Noir. We are planning on releasing V1 in 2025, just before the launch of the Aztec network. Right now, we have effectively a staging candidate for 1.0. And if you want to work with private smart contracts, go to Aztec.network. So we have lots of grants, lots of prizes for people who want to experiment with the state of the art. Right now, I think Web3 is in a bit of a stagnant place because what you can do with the smart contract hasn't changed in years. It's changing now. It's changing with technologies like Aztec. We're not the only ones, but obviously I'm going to show Aztec because I run the show. So yeah, try out our DevNet. This is very new and novel. Being able to do things like sign into a Web3 account using Touch ID, being able to transact privately, being able to build oracles like that validate things like TLS and entry, so you can get information from Web 2 into Web 3. This is all possible today with Aztec. So yeah, give it a shout. I have been Zach. I think this is the end of my talk. Thank you for listening.
Awesome, Zach. That was such a good way to kind of think about the whole narrative and just a good summary. So I really appreciate you kind of taking the time and actually us walking through the history of all this. We are actually a little bit over time, so I'm going to cut this short on the Q&A. But luckily, you already set the stage up for the next talk. And we'll kind of jump right in. So thank you. And for our next speaker, I want to bring on Yush to talk about ZK email and kind of how do we actually further that idea and help get identity also be part of this whole conversation. So Yush, welcome, and
Awesome.
I'll have you get started.
Cool. Thanks for the intro. Yeah, and great talk from Zach. I'm glad to be leading out from that. It set a lot of great context of the stuff I'm going to talk about. Sweet. Can you guys all hear me?
You are all good to go.
Cool. Great. Thank you. Sweet. So following, I guess, the lead out from Zach, I'll be talking a lot about specific ways, the specific problems that we see in crypto and Web3 and specific ways that us as ZK Email are trying to tackle that. And so the main problem that we were thinking about was that wallets are not intuitive. It's kind of the fundamental backbone and necessary precursor to interacting with any Web3 ideas, but it's very hard to think about hardware wallets, seed phrases, and interacting with blockchains. And we figured that the way that people are usually used to this is with signing with email or seeing things in their email. And nobody has yet figured out a really great way to make that very Web3 compatible. But it turns out that you can use cryptography already in emails. And if you can do that, then you can build something called ZK Email. And so I'll be talking a little about how that works and some wallet infrastructure you can build, such as signers and account recovery. A ton of people helped out with this work. You can see them in the top right. Not just me and Sora, but a team of 6 more people. And we're really excited about all the work that we're going to talk about today. So what precisely does ZK Email give you? Well, the idea is that if you can make proofs about any email you've sent or received, then you can build what we call programmably provenant data. The idea is that first, if you're verifying some email was sent, then you can verify that data from a Web2 mail service directly instead of having to trust a third party. It's programmable because you can extract arbitrary information via our ZK regex primitives. And finally, it's portable in the sense that whatever proof you make of that email or subset of that email can be proved anywhere you want, including on a blockchain. But like precisely what is happening when you're making a ZK email proof? So concretely, every email you've sent or received since 2017 is signed by DKIM. The DKIM protocol specifies that in order for spam prevention to occur, you have a domain with an RSA public key and an RSA private key. The RSA private key signs a hash of all of the information in the email. In this case, a SHA-256 of the from, the to, the subject, and another SHA-256 of the body hash. So what we do in ZK emails, we verify this whole process, the RSA signature verification and the SHA-256, and then we selectively reveal information from that middle section, the from, to, subject, body hash, with ZK regex. This allows us to selectively disclose different parts of emails when we want to disclose those parts of emails. You might have seen existing applications in the wild, such as ZK P2P, which allows you to verify Venmo emails. Concretely, you're saying, I've received an email from Venmo that has this sender and this receiver for this amount of money, and you keep all the other information in the email private. When you prove this on chain, you can then have that proof gate the release of money from an escrow contract, allowing you to on-ramp or off-ramp between, say, USDC and Venmo dollars. And you could do this for any other payment service that supports confirmation emails with the information of sender, recipient, and amount. You can also prove you own any social media handle because you receive emails with those handles. In this case, for instance, one demo we have is the proof of Twitter that allows you to show that you own any Twitter username by proving any email you've received from Twitter. You can do the same thing And we have proofs for GitHub and Airbnb and any other Web2 service that allows you to have that email. So the Airbnb one, for instance, you can reuse a KYC that you've done on Airbnb on any other platform. And finally, you can imagine that with the anonymity, you can prove partial things about yourself. For instance, that you only own an @berkeley.edu email, and then you can post on behalf of that credential without revealing who you are to anybody. And so this is what some folks at Nosy built, and it's quite interesting to see the social dynamics that emerge when you have anonymous organization-based proofs. So concretely today, what I'll talk about is email-based smart contracts. So the identity proofs are quite interesting, but we've already talked about them before, and there's a ton of information on our website. So today I'll be focusing on email-based smart contracts, specifically email signers. That is, imagine you have a large transaction, say $100,000, and you want to definitely have a two-factor authentication on that transaction. You can use emails directly on a Nosy-safe multi-sig. Second, we'll talk about login. It's quite hard to integrate OAuth even for normal developers, and to have it integrate with Web3 requires either giving up trust assumptions to a third party or accepting a very poor dev or UI flow. But today I'll be talking about ways you can use ZK email to have a very intuitive login system. And finally, I'll talk about account recovery. When you lose your wallet, it's quite difficult often to recover it. And so the idea that you can make social recovery really easy by having it intuitive via emails. Okay, so concretely to start, we'll just discuss how email-based smart contract works. How can you use an email to send a transaction? Well, the idea is that, remember, if we're making a proof of any sent or received email with ZK email, we need a user to send an email. And so how do we do that? They can authorize a transaction by just replying to an email. And we have a live demo of this up on Baseapolia at emailwallet.org. When you sign up, you'll receive an email like this, which is, account creation. And here I've put the code in the subject to view it easier. But you can imagine that in production, this value will be in the body, so that it'll be much more user intuitive. But this long code is actually quite important because what it offers is privacy and decentralization, surprisingly. Concretely, you never reveal the email address on chain when the email address triggers a transaction by replying to an email. The only thing that's revealed on chain is the hash of the email address and that long code. And therefore, the user's email is not actually revealed on chain when they do a transaction. Finally, or second, when you actually show that the user's email has the account code within the ZK proof, we prove that the user has that value. And so even if the relayer or whoever's doing the ZK proving goes down, you can ensure the user will never lose access to their funds. And finally, this means that the actual system, the relayer system that the user is replying to, that's doing the proving and sending on chain, can be totally decentralized. And you can get fault tolerance and censorship resistance out of the box because anybody with an account code can interact with any relayer. So what can we build with this? One example is a signer on a multi-sig, where you use an email address to confirm a transaction. Now, why do you want this? For instance, we've talked to some DAOs, and some problems that they've had are that it's very hard for all the users to access their wallets and immediately improve transactions. But if you had a very easy mobile confirmation flow, you can imagine people could just go into their email, reply confirm, and then move on with their day, instead of having to grab their ledger, plug it in, confirm, etc. And as long as you have main signers that have ledgers or hardware wallets or self-custody wallets, then you'd imagine that secondary signers might want easier confirmation flows. It's also much easier for people who don't have wallets or aren't familiar with the ecosystem to also be in control of funds. For instance, legal teams at companies, what we've often seen, prefer having email-based interfaces so that they don't have to maintain their own crypto wallets or learn about the space, but they can still participate in the ecosystem. And finally, you can imagine that you can build rules like, if I have any transaction of my very valuable assets or for large amounts of money, then I need a 2FA from my email. And so we've noticed that users in general, rather than learning about seed phrases and wallet apps, would much rather have a cleaner onboarding flow and then move to self-custody once they've understood exactly how to use it and what they're doing. So concretely, we have a demo on safe wallets with emailwallet.org, and I'll show briefly a live demo of how exactly this looks. So if we go to emailwallet.org and we sign in, then we'll land on a page where we can do things with our account. Now, concretely, what's happened is there's an address that's been deployed on chain, and this address effectively is a smart contract that is only controlled by a ZK proof. So it must receive a ZK proof from my email with a valid proof of account code. And this will allow me to effectively make a proof from there. So what I can do is I can take this address, note that it starts with 0xF14, and I can add it directly as a signer to my safe wallet. So I've done that ahead of time, but you can do that yourself as well if you sign up at emailwallet.org and just add that directly as a signer. And you can see on Safe Global, this is the exact same address, 0xF14. Sweet. And so now that I've added that, I can go and I can trigger a transaction from my wallet. In this case, maybe I want to send a few tokens to a different safe. Once I switch to my signer, which signer am I on? I'm on, let me see. I'm on 0xB3D on base Sibilia. Okay, sweet. So now if I go here and I send my transaction, sweet. Let's try sending to here. I need to check my wallet. Great, so what I've done is I've signed in with my primary EOA, and now I'm going to start the transaction that I want the email confirmation from. So I'm going to trigger that I in fact want to send this amount of ETH to this target address. Now you'll notice that I only have 1 out of 2 signers because the second signer was my email wallet. Now if I go to my email wallet, which is registered to this email address, you notice I've just got an automatic email asking me to approve this transaction. Again, we put the details in the subject so it's easy to see, but you can imagine it's very well explained in the email body. All I have to do is reply, and then once the relayer processes my email, generates a proof, and sends it on chain, it'll automatically approve that transaction. Until that happens, I can explain a little bit about what's happening behind the scenes. You can imagine that anytime a safe adds a signer that's an email wallet account, the network of relayers that are tracking email wallet accounts looks at that and picks up on the fact that one of these is a ZK email signer smart contract. It can then register it in the database, and you'll notice that when the safe triggers a transaction, then the relayer can pick up that there is a transaction in progress. Subsequently, the relayer can send that user an email exactly like the one we got, and then prove it on any prover, either that they run locally or in the cloud. Once I've generated that proof that in fact a user confirmed that transaction via the email that they sent, and they generate a ZK proof of that, hiding their email address on chain, they can then send that directly to Safe Global. And you can imagine this process that I went through of going to email wallet, signing up, and then putting that address in is a bit cumbersome. And so the hope is that directly in Know the Safe, we can allow you to enter your email address. So for instance, here, where you would normally have an Ethereum address or an ENS address, you can just put an email address directly, and Know the Safe can handle it behind the scenes. But we're still working on how exactly that's going to look. And so now if I head back to the demo, now that I've confirmed, I can go back to my Safe wallet, and you'll notice that the second transaction confirmation has already automatically been applied by that email reply. I can then execute a transaction from my main EOA owner, and that'll automatically send on chain. Sweet. So now that we've talked about how you can have 2FA confirmations directly on a safe multisig, I'll discuss briefly how we might be able to do intuitive email-based login. So you can imagine that this is a standard sign-up flow that people expect when they go to a website, that there's an email address, a username, and they can just continue. This is not the default for most Web3 apps. We've put up a demo at oauth.emailwallet.org of Web3 native email address sign-in with any email address, not just Gmails or JWT supporting emails. Now, when you sign up, you put in your email address, you'll get an email like this, which looks like sign in Sora on some device for some scope, in this case for 10 test tokens. Once the user confirms, then they'll automatically be logged in to that website. This is quite an interesting paradigm because this allows users to log into apps via a single email account, but have different scopes for different accounts. In this case, I gave this website access to 10 USDC only. It allows for very intuitive email-based login for users, something that they're quite used to. What is actually happening behind the scenes is that when you reply to this email, you're authorizing an ephemeral key to do transactions on your behalf for that scope. And that scope allows websites to not have unilateral control over your funds, but only the amount that you want them to have control. Now, it turns out it's really easy to set this up. If you have a JavaScript frontend, it's effectively 2 lines where you specify the email and username the user just put in, the amount of time you want to request. For instance, you could scope that you only have access to their account for a week, and the token allowances. In this case, we asked for 10 tests. And subsequently, when you want to execute a transaction, you can just specify the address you want to execute to and the payload, and it'll automatically execute that transaction for you. Because it's only 2 lines, it's actually easier to integrate with Google OAuth. It gives you full security of a user's email domain. You don't have to trust any third-party service to verify those emails. The scopes are shown upfront to a user, and it's totally decentralized. And so the docs show exactly how to do it and what it does, but we're excited to work with more folks to see email-based OAuth in the wild. And again, I'll let folks go to oauth-emailwallet.org if they want to check out more. And finally, I'll talk about email account recovery. This is quite interesting because it allows you to use email guardians to recover your account. Concretely, what does this mean? Well, currently, you need people, all the guardians on your account, to have seed phrases. This is often quite unintuitive for folks because the people we trust the most, for instance, our friends and family, are often not yet on board into Ethereum. And so it'd be nice if we could allow them to use their emails to be our recovery signers. It's nice, again, because those emails are not revealed on chain, and so users have an expectation of privacy. And you can recover any smart account or safe because we've made this really easy to integrate with any existing smart contract, including all of these wonderful smart contract wallets. Concretely, it's quite curious because social recovery is one of the few things in crypto which has not yet fully been figured out. And it's quite expensive, especially security-wise, if you lose all your funds and you don't have very intuitive recovery methods set up. And so concretely, what we can do is any smart account that's 7579 compatible can have an intuitive 5-line integration flow in which they simply call install module on the ZK email module. It's 437 compatible because you can install it via permissionless.js in your front end. And it's decentralized because smart contracts can be called by any valid relayer with an account recovery proof. And even if you're not 7579 compatible, you can integrate it quite easily just to specify a couple extra functions. Concretely, if you, for instance, are a wallet and you want to integrate account recovery, you would define some configuration like this, that you want to recover some account, in this case, this Ethereum address, to a new owner, this Ethereum address, with some recovery module, this Ethereum address. And you can imagine that users or apps can customize this completely in just these roughly 10 lines of code, where they specify concretely the subject template that they want to appear in the subject. And then our Solidity library will automatically handle sending that email, receiving the reply, parsing it into this format, and then providing those 3 Ethereum addresses as call data back to the requested function that defines the subject template. So concretely, now that we've seen how people can configure it for their wallets, how exactly does it work? What is happening behind the scenes is that a user will install the recovery module. They'll set their email guardians, and the threshold and the time lock, specifically 2 out of 3 guardians, may be delayed by a week to give the user a chance to respond if they still own the account. Then guardians can accept being a guardian. So for instance, once I've set a bunch of emails as guardians in my wallet, they simply reply, and we can ensure that they have access to that email and that they're able to reply properly, preventing broken recovery setups, which is really important for having good security. At some point, you lose your main signer. Maybe it's your phone, maybe it's Ethereum wallet, maybe it's your passkey, but now you're forced to use your recovery signers to recover all of your assets. Subsequently, all of your guardians receive a request, hey, do you want to recover this user's account to this new address? And once they reply and the threshold is met, then you can start completing recovery once the time lock elapses. This protects against malicious recovery attempts because the time lock means the original owner can go like, hey, something's wrong. I've not lost my account, actually. I'm going to cancel this and change all of my email guardians. So concretely, if you go to prove.email/recovery, so I'm going to head to the safe wallet and into prove.email/recovery, I'm going to go into the safe wallet flow. And you'll notice that I've already connected it to my safe wallet, but it's quite easy to do via Wallet Connect. I'm going to enter my Guardian email. In this case, on this new safe, in which I'm the only signer, I'm going to add zkemailverify@gmail.com as a recovery signer. The time lock will be 1 second, so I can demo this. And I'll simply configure this on the safe website. So if I go back to recovery, let me disconnect and reconnect my wallet. Sweet. So I'll show you the whole flow where we start with the Wallet Connect URL. So you plug it into the UI. And now you'll notice it's connected to the safe email recovery flow. When I start this flow, now I can set the email I want to set as a guardian, and I can configure that. What will happen is back in the safe website, it'll automatically start a transaction, which is saying, hey, are you sure you want to execute this transaction? Once I connect my wallet, then I can simply execute. And now what I've done is it's going to add the zkemailverify@gmail.com example email I've specified as a signer. We'll give it a second. And you notice that in that email, I've got an accept Guardian request. Now, again, we've put the hashes and address in the subject to make it easy to see the information that actually matters, but you can imagine in the body, it more clearly sets it out. Once again, I can just reply confirm, and it'll confirm my status and then add me directly as a signer. Now, when I request a new wallet address, maybe I've lost this B3D account and I want to instead move to this new signer 5CE. So what I'm going to do is I'm going to say, hey, I've lost my account. Anybody can go in and specify, hey, the new wallet address for this safe should be 0x5CE, and the recovery will get triggered. Now, I can check my email and simply reply to confirm just like we did. But perhaps for time reasons, I'm going to just explain what exactly happens, and we can come back and check how that goes. So concretely, when the owner configures recovery via the front end, the relayer emails the Guardian to confirm acceptance. The Guardian replies to the email, and a ZK proof is generated. And then on-chain, which is the bottom half of the screen, the proof is verified, and it automatically interacts with the ZK email verifier. When you want to process the recovery, you do the exact same flow. The owner or Guardian starts a recovery attempt in the UI. Technically, this could be anybody because the owner's lost their account. We don't know they're the owner. The relayer will send an email to a Guardian. The Guardian will look at it, make sure it looks good, and then reply to the email again, generating the ZKP. Again, it'll get sent on-chain and process the recovery for that account. So if I head back to this demo, now that we've triggered this recovery, you'll notice that the acceptance has succeeded for my Guardian request. And if I trigger the recovery, again, so I can simply specify this was the signer on my email, and this was the recovery address that I wanted to set. Now, when I go back to my inbox, you'll notice that now that my recovery has been set, I can get to this email, which looks exactly like the one we specified in the subject template, where I specify the account I want to recover, the old owner, the new owner, and the ZK email recovery module. That all looks good to me. I can say confirm, and back in the safe wallet, it will now automatically be rotating that signer once the threshold has been reached and the time lock has been confirmed. And so far, we've talked about all of these different ways that you can use ZK email to trigger different smart contract ideas, but proofs can be much more general than that. You imagine you're not proving just any email you're sending to trigger on-chain functions, but any email you've received. For instance, one thing Liam asked for earlier was, imagine you could prove you got an email from karthik@gmail.com. And so in 5 minutes, we added a new ZK proof via this registry on the left that allows anybody to prove that they got such an email. It was super easy to specify. In the UI, it guides you through how to construct this kind of specification, but in about 20 lines of code, it's JSON specifying, hey, I want to take out the subject, make that public of the email. The maximum length is about 93, and the sender should be ethglobal.com. then I can verify that I in fact got an email from ethglobal.com and reveal the subject. For instance, maybe I got accepted to a hackathon, and now I can prove to everybody that I got accepted to a hackathon without revealing which hacker I am. And it turns out that this only took a few minutes to deploy because the UI allows you to lead you through this. And we're really excited to see the explosion of proofs from people just specifying JSONs to then compiling proofs in all sorts of different languages, including currently CIRCOM, but soon Noir, as Zach mentioned, and even ZKVMs. We're excited to support folks building all sorts of different projects. You can imagine the rabbit hole runs much deeper. You can trade restaurant reservations by proving that you had a confirmation email that transfers the reservation. You can whistleblow and put bounties on those whistleblowing. You can donate directly to email addresses, say in papers or for airdrops or anything else. And there's so much possibility here that we're excited to support any folks building this kind of thing. There's tons of research we still have to do, building all sorts of weird new circuits, verifying they work for all sorts of weird protocols, and in general, making progress in space on these novel ideas. And finally, we have lots of infrastructure directions we want to build. For instance, people building real ZK versions of Etherscan, compiling proofs, large proofs in the cloud, or building out some more infrastructure. And broadly, like Zach mentioned, there's a lot of surface area for Web 2 data to become interoperable on Web 3, but it requires there to be signatures in that data. So for instance, we ran a short residency in May called SigSign.com, in which we effectively had a bunch of teams together and we tried to make proofs of signatures. You can imagine that there's a ton of really interesting ones. For instance, if you can do DNSSEC, which is basically signed DNS, you can now get any DNS value on chain, including your DKIM public keys. If you have SXG, you can get any website front end directly approved on chain without having to trust a middleman. But again, you have to have the signed exchanges enabled on the website. You can again imagine you can prove passports. So for instance, Open Passport lets you prove the government signature on your passport and then verify you're over 18, for instance. And you can verify any legal document on chain by automatically proving that you had a signed PDF from DocuSign, which is actually cryptographically signed as well. And so, for instance, you can imagine the same primitives that make ZK email signature verification, hashing, and regex can be applied, for instance, to SXG. In this case, which is applied to a website, so now I can prove any information from vibs.wiki directly on-chain and interoperate with it. Maybe I can prove that he published some post, or I can prove that he's posting on some schedule or something like that. So to wrap up, we're excited for folks to ask questions. Feel free to reach out if you want to build something. We had an ETH Global bounty at ETHCC, and we'll again be judging ETH Global, ETHOnline. Our audits have already completed on most of the primitives, and we're doing a second round of audits on the account recovery in September. We already have a version on mainnet with Sol, and Clave will be on mainnet soon. And you can make general identity proofs and learn other stuff that we're doing at prove.email, including making ZK proofs of any email in your inbox. Sweet. So thank you for listening, and I guess we're almost exactly at time. So I'll let Karthik and I'll decide if we should take questions.
This was awesome, and thanks for actually kind of showing cool demos. Like, it's always great to see things working, not just the ideas. I don't think we'll have too much time for questions, but I'll just kind of ask one, which is going to be a very kind of common theme here, which is all this stuff is super useful. You've kind of shown and demonstrated that it's actually valid and helps address a lot of these cases. But how do you think about the interfacing here from the point of view of like what happens on multiple devices? And it's just not just like I have two sessions on two computers, but also like what does the mobile interface look like here, and how do you kind of get the same experience without having to kind of compromise on how you actually just operate day to day? Like if I'm traveling, if I'm just with my phone, do I miss out on all these features, or do I have to have my desktop and a Chrome extension or something with me? What does that evolution look like?
Yeah, it's a great question. So I think one of the things we've prioritized is that it shouldn't be the case that you can only do it on a desktop, and you shouldn't have to download any Chrome extension. So the only thing people need to do is receive emails and reply to them. And so we've thought a lot about how to have such a clean UI, because yeah, you're right. Like most of the time when you have a wallet, you need to have an extension, you need to have like a ledger, you need to have like a concrete device for which it's tied to. But in this case, this is really the only thing I've seen so far that is completely interoperable with all your devices out of the box and doesn't require installation of anything, just existing email which users already have. And so yeah, it's a great idea. And when you want to prove things from your email, so for instance, you want to maybe do some identity verification proof, again, you can just sign in with your email and then click the email you want to prove, and boom, it's done, in case you want to do that in any verification. But if you want to interact with any of the smart contract triggers, replying to an email is enough. And so yeah, you're totally right that I'm very excited to see how folks interact with this when the UI is so much cleaner and more portable.
Awesome. No, this is great. Well, thank you so much. And yeah, check out some future bounties too here. You're going to have a lot of people kind of build on this, and I'm excited for this whole ecosystem to get bigger and bigger. So
yeah, thank you.
All right, with this, we are ready for our next talk. And for this one, I'll bring on Michal to talk about Snark miniaturization. So without further ado, let's welcome Michal here. And whenever you're ready, we can get started.
Hi, hello. Yeah. Let's go to full screen. Okay, so today I would like to talk about Snark miniaturization. My name is Michal. I work at Nethermind Research. So, okay, you're probably familiar with zero-knowledge proofs, but at least let me use this slide to introduce some notation and some graphics that I will be using throughout the presentation. So on the left, you have a prover here, like a humanoid robot that wants to show to verifier here this like metallic box that some statement is correct, right? And the statement is X, and there's some additional witness that proves that the correctness of the statement. So in case I usually just presented a ZK email, so you may think like, okay, so the prover shows like the possession of particular email address, and witness might be some secret data that accompanies this ZK email. And finally, like the verifier who is given only X, that the original statement, need either accept or reject the proof. Okay, so in terms of miniaturization, I would like to talk about like 3 different kinds of miniaturizations. So actually, I would like to start from the right, sorry. So verifier compute, okay? So this is actually very important when you need to settle your proofs on chain, right? So you can imagine that you have some Solidity smart contract that is your verifier that verifies the proof, and you want the Solidity smart contract to be as light as possible because gas costs money, and you don't want to pay too much for proof verification. Okay, and here we optimize for verifier computes. And I would say that this is like the most use cases we see right now, utilize snarks that are optimized for short verification computation. Some examples are our beloved Graph16, but we also have Starks here, 2 new schemes, Polymath and Pari, and also well-known Plonk. Okay. On the other side, we can think about minimizing proof size, and this is super important when storage matters. I'm not sure there's like that many use cases for it right now, especially in Web3 context. I think like verifier computation is a much more important right now. But nevertheless, the list of proof systems we have here is relatively similar to what we have for verifier computation, right? So we have like Graph16, and there are like 2 very new proof schemes that are, I think like they are not even like 6 months old, Polymath and Pari, that are even more proof size efficient than Graph16. Finally, we have Plonk that is not as good in proof size as Graph16 or Polymath, but still like is the size of the proof is relatively reasonable. Finally, we have snarks that are optimized for prover compute. And I claim that this category of proof system is super important for real-life applications. However, I would say that this category of proofs is also not that well studied. And I think like the biggest bottleneck here is that usually the cost of very efficient proof systems is huge verification cost that comes from like large proof size or large verifier compute. And here some examples are Hyperplonk, Breakdown, and Orion. If you haven't heard about any of them, it's definitely not your fault. Just like the other snarks are much more popular. Okay, so to be a bit more concrete, I divided these proof systems into three categories. So first of all, we have pairing-based snarks like Graph16, Plonk. So prover compute is n log n. So this comes from the fact that prover needs to interpolate a very large polynomial that represents computation, and interpolating polynomial takes n log n time. Okay. On the other hand, we have proof size that is like that is super short. So in case of Graph16, it's like 3 group elements. So it's like super short. And verifier compute that is also like constant. Second, we have Fry-based Starks. So here we have like all these Starkware products, if Stark, Silker Starks, but also Polygon's Plonky2, and like many variations of Fry-based Starks, like with different fields, different commitments. So here, prover is still bottlenecked by the fact that it needs to perform some interpolation. So still proof computation is n log n. However, it's like a bit quicker, say, than in pairing-based snarks. This is like usual situation. So this comes from the fact that prover in snarks needs to compute easier operations, let's say, like hashing, like small field operations instead of large field operations and group operations. In Stark's proof size is like much larger. It's like logarithmic to the size of the proven instance. And in terms of, say, Starknet, it can goes to like hundreds of kilobytes. And verifier compute is also worse than in snarks, and it also depends on the size of the computation. Thankfully, the dependence is logarithmic. So finally, we have the super efficient snarks in terms of proving time. So Hyperplonk, Breakdown on Orion, and a few others. So prover compute is actually linear, and this comes from the fact that some other cryptographic primitives are used to instantiate them. So I said that in like case of pairing-based snarks and Fry-based snarks, we usually do interpolation of a polynomial. These polynomials are univariate. In case of Hyperplonk and Breakdown, we do multivariate, multilinear polynomial interpolation that is actually linear. The price we pay here is proof size and computation that is required from the verifier. So the proof size is roughly square root of n. It doesn't need to be like exactly this, but I want to show you like the order of magnitude, like how much worse there are compared to other schemes. Actually, maybe I think like I picked the wrong color here. It shouldn't be orange. It should be like very red here, like to show like how bad this can be. Okay, so the question I want to discuss during this presentation is, can we combine the best of both worlds? Can we have both fast prover and efficient verification? Okay, so let's start with speeding up the prover. So we'll focus on these snarks that that prover can be made more efficient. So like pairing-based snarks and Fry-based snarks. And before we continue, I would like to introduce a concept of continuations. So on the left-hand side, we have this machine, this robot that needs to prove some relation RXW, right? Like to have concrete example, it could be proving ZK email, proving email address possession. On the right-hand side, I represent this program as a table. So how to read this table? you can think that in rows, like columns denote registers, so memory cells in the CPU, okay? And rows correspond to time. So if you think that, like the computer makes some steps, so you can think that in the first step, the computer has state A1, A2, A3, A4, then it makes the next computational step. It goes to B1, B2, B3, B4, and so up to E1, E2, E3, E4. Okay, and this relation that the prover needs to prove is this transition from vector A to vector E. And that can be like a relatively large transition. So for example, it could be like 2 to the 20 computational steps. So it's like a huge number. So actually, we can observe that this complicated transition can be broken down into smaller transitions. So instead of having like this one big transition from A1 to E, so from A to E, we can introduce like intermediary relations. So for example, instead of proving that I went correctly from A to E, I can prove that I went from A to B correctly, from B to C, from C to D, and D to E. And this actually has can give us some pretty significant speed up. So how do I do that? I use something called folding. So idea here is that I take two instances of some size n and collapse them into a single instance of the same size n, right? So I reduce the size of the instance of factor 2. So we may think like, okay, so we have like two transitions to be proven, say from A to B, and this is represented by R at X1, W1, and from B to C, and this is represented as R at X2 to W2. So here we collapse these two transitions and create a single like collapsed program that shows that both of these transitions were correct. Okay, so what I'm proving here is that the relation R on X prime W prime, so this collapsed relation, is correct, is true, only if both of Rx1 Wi and Rx2 W2 hold. So how can we use it in practice? So yeah, let's have an input that is of size some m times n, and I will be collapsing like consecutive relations, consecutive continuations into smaller instances. With every step, I reduce it by a factor of 2. Okay, so I start with R at X1 Wi, and I collapse it with R at X2 W2, and get R at X prime W prime. Similarly, I get R X prime W prime, collapse it with Rx3 W3, and get Rx bis W bis. Eventually, I run out of like these continuations, right? So I have some final relation Rxm Wm, okay? And this is the relation I'm proving. So this is like a super, it could like save a lot of time for the prover, because now the prover, instead of showing this super big relation Rx1 and Rx2 and Rx3 and Rx4, it just shows like one collapsed relation that is of a much smaller size. So if you are interested in this concept, you should check like Nova, Hypernova, Protogalaxy, or more. And to be more concrete, like this prover computation is reduced from nm log nm, right? Sorry, like m should be small and n should be capital, right? So this is like the proving time when I naively prove the whole relation to n log n, with some caveat, because like I also need to pay for folding, right, and proving that folding was performed correctly. Okay, so now I will talk about minimizing the proof size. So I think this is a more interesting case. So our initial proof system is this proof system with linear prover. So we have super efficient prover, but like the proof sizes and verification times are not great. So here we really talk about proof miniaturization. So let me explain this picture to you. So first we have some breakdown prover. Breakdown is one of these linear prover proof systems that needs to prove some huge relation. Okay, it does prove it. It outputs some fairly large proof pi. So now, I don't want to verify this proof by, say, on-chain, because yeah, I would pay like hundreds of dollars like for the compute. What I do next is that I take another breakdown prover and I ask him to prove the fact that pi is a correct proof. Okay, so this is sometimes called like proof recursion. So this proof, the second prover runs a circuit for breakdown verifier, this little box in this white square, and I show that, and the prover shows that this verifier would accept the proof pi, the original proof output by the first prover. I can repeat this operation multiple times till I have proofs small enough, and eventually I can settle this proof here p prime, say on chain, or just verify it using fairly small verifier. And this technique is not limited only to linear proof systems. They are used in, say, in Starks, for example, right? I think like Polygon is using this. So they have like a very large Stark instances, and they recursively compose them such that the final Stark, the final proof is small and very light to be verified on chain. Okay, so to show like some concrete improvements, let's take a look at these numbers at the bottom left side. So we have input instance of size n, breakdown verifier of size m. So here is I'm saying like m is the size of the verifier as an instance, right? It's not like verifier time. It's like the size of like how many steps in this table I need to do, like to make the to run the verifier. And usually m is much smaller than n. So now the prover compute is O at n plus O at m. Okay, so this is actually like a bit larger than O at n, right? And like the fact that the prover compute increases is very simple. I run 2 provers instead of 1. However, the final verifier compute is square root of m. So square root of something much smaller. Okay. I can use this trick with composing, like say, breakdown provers, but I can also do something a bit more tricky. So assume that we have 2 different proof systems with 2 different trade-offs. So on the left-hand side, we have a breakdown, efficient prover, big proofs, slow verifier. On the right-hand side, we have, say, graph 16, so n log n prover, so slow prover, small proofs, and very fast verifier. So I actually can combine both proof systems, such that like the initial relation, this very big program will be proven by this super efficient prover from breakdown. And then the proof that is like much smaller than original instance will be proven by this small, less efficient prover from Graph16. What it gives me is that this Graph16 prover outputs a very small proof. It outputs a Graph16 proof, right? That can be easily verified on-chain. And what I require from this Graph16 prover in the middle, I require it to prove that the proof output by the breakdown prover on the left was correct. So let's take a look at the table with some numbers. So input instance is of size n, breakdown verifier is of size m, and so prover compute is now O at n. So this is like the first prover plus m log m. This is like the what Graph16 prover introduces, but the verifier compute is constant. Okay, so why do we care? Okay, so like, you know, to tell you like a grand vision, why should we care about real life proving? I would say, okay, imagine a world where you have robots that go along humans, right? They are not like robots in factories that are behind laser fences and like nobody can approach robots because like the alarms go off. Imagine a world where like robots are just roaming freely. So in that case, we need to have some kind of mechanisms that would keep these robots in check, right? So like that will ensure that the robots are not doing anything harmful for humanity. So here you can imagine that the robot can constantly proving that it behaves correctly, and if like some proof is not provided on time, then the robot is like is switched off, right? So there's some in-check mechanism. But and this is like a very futuristic vision. Real-time proving and like proving is not efficient enough to realize that we still don't have robots roaming on the streets. So let's think about something more deployable today. So think about proof systems for mobile devices. Think about like all these things that you would like to prove using your handheld phones. So think about like, this is like super standard example, like verifiable credentials, right? You want to show your age, I don't know, in a bar. You are not going to take your laptop to the bar. Okay, like we all take laptops to the bar, but like you are not going to show the laptop to a bartender, like to certify your age. And this can be done in privacy preserving manner, right? You can also like show I don't know, citizenship. You can show your driving license and use some on-chain car rental place. You can show your university diploma and also and show that you are eligible for a job, or like you are qualified enough for a job without revealing like who you are. You can make private transactions like Zcash, right? You can manage your wealth. You can use some proving location services or like any application you can imagine. So in this presentation, I think like I think about like it's a bit of call for action. So you're hackers, so please play with like exotic proof systems because like the trade-offs they offer might be just right for your applications. So on the right, I listed some, I say, exotic proof systems that are not that popular in deployment now, but they all have like the code that you can play with and see like the trade-offs and see which one fits you. So thanks a lot. This is a QR code if you want to learn more about Nethermind research.
Amazing. Thank you so much. I think this was a surprisingly not super technical as I thought it would be, and because I was scared to go, wait a second, we're going into formulas, but no, it was actually very easy to follow. You did a really amazing job at making that really simple to kind of really follow. In terms of kind of at least understanding kind of how we should think about optimizations, how much of this is like we need to invent new things versus a lot of this is about just like something like compiler optimization that kind of gets us to the next stage and simplifies and makes things faster. Where are we on the application of these proof systems into kind of building something that is simple and fast?
Mm-hmm. Yeah, great question. So I think like there's still a lot of things to be done on every stage, to be honest. Like, as I said, like this linear proof systems are usually not that well known. There is quite a little benchmarks. So I'm trying to encourage people like to see like, okay, like how efficient they are in real life. I think like we still don't know that. And there is like a huge research space there, like, like very theoretical cryptographic research that also uses some very sophisticated coding theory to push this area forward. But there is also a lot of things to be done on engineering side, like providing like a better compilers here, like better DSLs that would allow us to use these things like more efficiently.
Nice. I think that's kind of all we have time for in terms of questions. So thank you so much. I think one other thing that would be very helpful is if we can get a copy of your slides. We'll kind of give this to everybody in the audience too. We'll kind of link that. So whenever you get a chance, just send us that link, and we'll publicize this for everybody to also follow. But also for everybody who asked for that, don't worry, you can just rewind on this live stream and also kind of pause on your favorite slide, but we'll kind of get you the copy.
Thanks a lot.
All right, thank you so much. All right, with this, we are ready for our next talk. For this, I'd like to bring on Remy from Inco to talk about how verifiable computing is making a impact on making FHE more and more practical. So without further ado, let's welcome Remy.
Hi, everyone. Excited to be here. Thank you, Kartik. So today I will be speaking about the topic of FHE, its novel use cases, and then roughly speaking what we're building here. So, what we're building at Inco is what we call the Universal Confidential Computing Network. And so I'll start with the problem statement, which is today all the L1s and L2s have one thing in common, is that they're all public and transparent databases. Now, we do believe that there needs to be a minimum of confidentiality that's necessary to drive mass adoption. So a couple of examples. If you imagine billions of people coming to the public blockchain space today, it would actually be social chaos because everyone's bank accounts and payroll system will be completely public and transparent to everyone. Now, institutions and enterprises have also tried to come into the space for the longest time. They've tried private blockchains such as Hyperledger Fabric, R3 Corda. It's just not quite the same because private blockchains are fundamentally almost like private servers. They don't get the same level of interoperability, but also not the same user base. And so oftentimes these institutions and enterprises have compliance reasons, but also trade secrets. So it doesn't quite make sense for them to build on fully transparent databases. And then lastly, there are just a lot of use cases that wouldn't make sense without hidden information. So think of all the card games, things like private voting or blind auction. So the cryptography we're working with is called fully homomorphic encryption, FHE. For folks who have never heard of this term before, what FHE really does is the ability for you to encrypt data, but also still compute on top of it without having to decrypt. So if you're non-technical, imagine the ability to encrypt a picture like the cat picture below. You can still modify the pixels by modifying the RGB values by essentially doing math on top of these pixels. And by the time you decrypt, now you have a filter. So this is really kind of the core essence of what FHE does, is really the ability to encrypt data, but still allow you to manipulate this piece of data without revealing what this is. Now, FHE has had a pretty long timeline. The first idea was actually introduced back in the 70s with this idea of privacy homomorphism. So back then, this was really just a wild dream, a fantasy. Just, what if we could encrypt data and still compute on top of it? The first, I would say, introduction to FHE or partial FHE with homomorphic encryption was in '99 with Pascal Pallier. The idea is that you could encrypt data and do simple additions. But this overall was still very fundamentally limited. The reason why there has been such a big limitation with FHE is the way FHE works is that, as you can see on the left, is the idea that you can encrypt data. So you have the actual data, some data padding, some noise, and some noise padding. The challenge is, as you do computations on top of this, what we call ciphertext, is this noise would keep on growing until this ciphertext is no longer valid. So one major breakthrough that happened back in 2009 was with Craig Gentry, who introduced this concept of bootstrapping. So you can think of bootstrapping as a way to basically denoise in between operations to basically keep this noise in check so that you can keep on performing basically operations on top of the encrypted data. But this process was just basically taking a lot of time. So it wasn't very practical. The second breakthrough happened in 2021 with this concept called programmable bootstrapping. So what programmable bootstrapping really does is a fast table lookup that makes this bootstrapping process a lot more efficient in only tens of milliseconds. And so from here, you can have a lot more practical application in FHE where you can do all sorts of more complex operations, but also keep on getting this noise in check in between operations in a very fast manner. So you can, in the context of smart contracts, you can basically do multiple series of FHE operations without having to worry about this bootstrapping issue. And then lastly, there are also hardware accelerations coming up pretty soon in the FHE space. So folks have been working on hardware acceleration for quite some time, actually. Even back in 2021, DARPA gave funding to Intel and Duality to really just pursue hardware acceleration for FHE. And there are also dozens of companies who have been looking to the space. Also, some ZK companies have been looking to supporting FHE as well. That are coming out next year. So, what makes FHE really stand out compared to some of the existing solutions around privacy that are ZK-based is really around this idea of composability. So confidentiality has never really been composable before. And what this really does is it allows you to store encrypted data on-chain, but also allow anyone to interact with this in a permissionless manner with this concept of a shared state. So if you think about most of the applications we use today in crypto, whether it's DeFi, whether it's gaming, we need to interact with some kind of shared state, whether it's a liquidity pool or some game state. And so FHE here offers composability because its form factor resembles very similar to your typical blockchain states, but you're just storing encrypted states, but you can still compute on top of it. ZK, I would say, is a more private solution in a sense that, oftentimes when you use ZK for privacy, you're storing your data off-chain on the client side. So it actually never leaves your clients. But the challenge here arises when you need to enable a use case that involves multiple parties. So, do you have this prover and verifier setup where, if you need to coordinate states, you need a centralized prover to sort of do the state transition on behalf of everyone. So it's just a very different type of form factor that ZK can enable. That it's, I would say, a little bit less convenient in terms of composability. Now, the previous side might sound like it's really ZK versus FHE, but in reality, we also use ZK here in the overall architecture. So really, to make FHE work, or for FHE to be more robust, you also need this MPC and ZK components. And so I'll just quickly touch upon how these different cryptographies are being used. So MPC here is reused for decryption purpose. The idea is that in FHE, everyone encrypts their data under a same public key. That's a shared public key. And this public key is ideally generated through DKG, so some kind of decentralized manner, where the private key of this public key actually never doesn't exist. It's essentially done in a decentralized manner. And so for any piece of data that you need to decrypt, you essentially ask each of the key holder to do a partial decryption. And once you reach enough of the threshold, you're able to decrypt the plain text. And on the ZK side, essentially what you do is, if you need to encrypt data in your browser, you actually need to prove two things. One is you want to prove that you know what the plain text is. The reason why you want to do this is you want to avoid people front running, just copy pasting your ciphertext and front running you. And the second thing is you also want to prove that the ciphertext is correctly formed so that the FHE operations doesn't run into issues. And then lastly, FHE here is really used to handle the computation side of things. It doesn't need to decrypt, and this is really sort of like the beauty of this cryptography is sort of decoupling the confidential compute with the decryption. So when you apply FHE into an EVM, it's the way it represents itself, it just encrypted types, right? So in the simplest form for ERC20, it's just the mapping of address to an EUINT for your balance. So this is the amount of tokens you hold, but this is represented in the form of an encrypted integer. If you think about the way we build applications in Web 2, typically if you want to hide some data, what you do, you just shield this behind a server. But blockchains are actually public databases. So the only way for you to shield data is actually through encryption. So this is where if I want to hide my balance, I just encrypt it, and this now becomes a private state or a private piece of information. If I need to do an ERC20 transfer, it's also very straightforward, because what you're doing is you're adding an encrypted amount to someone else's encrypted balance, and here you're just reducing your own balance by this hidden amounts. So everything happens on chain. The encrypted states are stored on chain. It doesn't require you to have specific hardware. Everything is cryptography based. It doesn't require you to write complex circuits. It's just solidity. And then lastly, you don't need an additional off-chain coordination layer, because you can directly interact with the smart contract and use basically the blockchain itself as the shared layer that I mentioned earlier. And then lastly, we are also able to generate randomness fully on-chain using FHE. This randomness is actually hidden. So basically, it's quite essentially quite useful if you are into building games and such, to have basically native randomness. So with this, we believe this is the next frontier. The reason why we believe this is the next frontier is because of all the net new use cases that we can enable across different verticals, including DeFi, gaming, asset management, infrastructure. A lot of times people think that what we're building is privacy, but privacy is ultimately just a very small subset of what you can do. A lot of these use cases, you think about the card games or even private voting, has nothing really to do with privacy. It's really fundamentally the way we build things in Web 2 cannot come to Web 3 unless there is a layer to hide information. And so this is where we believe this is sort of a missing primitive. And just like how Chainlink enabled novel DeFi primitives to unfold, like the money markets, derivatives markets, we believe that the next frontier here really is enabling encryption to existing public blockchains, and from there enabling net new use cases that weren't feasible before. One use case that I like to typically present is very simple. It's just confidential ERC20. So we've seen some of this a little bit earlier. The idea is you can hide your balance, you can do transfers. So if Bob sends money to Alice, only the amount is hidden. What makes this really different from something that's legacy, more, for example, something like Tornado Cash, which hides the sender recipients, is because in FHE everything here happens on chain. You can actually see on Etherscan, for example, that Bob has sent money to Alice. So you can trace the flow of funds, just not the amounts. And so this is actually quite interesting as a user experience, because it's very similar to what folks have been using in Europe, like Revolut, where you can see your friends sending money to each other, just not the amounts, or something like Venmo, which is the same experience. And if you think about this experience specifically, it's not even about privacy, because these are not even labeled as privacy apps in the Web 2 world today, right? They're just basic payment apps with a minimum of confidentiality. So this is just one example to illustrate how payments could look like in terms of user experience. Another use case is just card games. So we're all familiar with poker. It's crazy to think that we still don't have fully on-chain poker in the crypto space. Poker is a bluffing game. It wouldn't make sense if everyone has perfect information, right? So you need the ability to hide the cards. And more importantly, you also need the ability to generate the cards. So VRF, I would say, have existed for quite some time in the crypto space. But the challenge with VRF is that they provide you plaintext randomness, which in this case, you actually need to be able to generate hidden cards, because it's a bluffing game. Another game that we essentially first built last year, actually during ETH Global NYC, is really just this on-chain mafia game. Here, this is also a bluffing game. Basically, you have 4 or 5 players, and then you can have a player who has a hidden role, which is what we call the mafia or the killer. And so the player has to bluff his or her way until the end of the game and try to vote everyone out and survive, essentially. And again, this is a bluffing game. You need to be able to hide information. And also, this is a multiplayer game. So you need a shared layer for coordinating the game states. So this is where, because this game is on chain, it's just very easy and very straightforward to implement something like this. And this game wouldn't make any sense on something like Ethereum or Polygon without any ability to hide information. And if you think about all the crypto games that we have today, there is definitely a lot of room for improvements. If you think back of all the games that you've been playing, growing up, the games that are the most fun oftentimes require additional challenge because, you have to, you can conceal information, you can conceal your stats, conceal your resources. You can also basically bluff. You can also form secret alliances. This is really sort of the type of experiences that we are missing today as a whole. And we do believe that, the ability to encrypt information and selectively reveal them would really also push for the kind of like the next types of games that can be feasible in this space. Another vertical that's also quite interesting is really this idea of identity. So today, all the identity solutions oftentimes are some kind of soulbound token where you would KYC with a party and you receive a soulbound token that attests certain insights about your identity. So are you over 18? Are you in Europe? Do you have a good credit score? This is quite inconvenient because all this information is basically public at all times. And this information can also change. So one thing you could do with FHE is actually the ability to do comparisons over encrypted data. So there's this idea of a dynamic DID. The idea is imagine storing your age or your location or credit score in a hidden manner, but you can still selectively reveal insights about your private information without revealing the actual information. So maybe for a casino dApp, I just want you to know I'm over 18. Maybe for a money market, I just want you to know have a good credit score and nothing else. So this experience is actually very similar to what we have again in Web 2. So if you think about Google Auth, when you connect to a application, you can say, I want you to access my calendar, maybe my contacts, but not my Google Drive, right? So again, this is also just the idea of moving a lot of the Web 2 experiences to Web 3 that wouldn't be feasible unless you have the ability to shield certain information. And so the way this presents itself is pretty straightforward. So with FHE, you get to do comparisons. So what you're doing here in practice is a tfhe.gt, meaning greater than. It's a comparison. So you're comparing whether or not a credit score of a user is above 700, and then you decrypt that specific insights. So you can imagine this where you could have a money market that only accepts users with good credit scores, and then they don't have to necessarily know the entire credit score. They just need to know this specific insight. And this credit score could also change months over months, right? So maybe this time when you query, it returns true. The next time you query next month, it returns false. So you don't have to essentially always issue a new soulbound token. You have this concept of dynamic DID that I mentioned earlier. So because of a lot of the form factor of FHE does resemble sort of like your typical blockchain states, when you implement this into the EVM, one of the biggest benefits is that you are still compatible with existing Ethereum toolings. So Hardhat, MetaMask, Remix, making it extremely easy for existing Ethereum developers to get started. And FHE today actually offers quite a big range of operations and comparisons, right? So you can add, subtract, multiply, divide. You can do reminders. You can also do bitwise operations, right shift, left shift. You can also do all sorts of comparisons, like that DID example that I mentioned earlier. So really, it's up to you to go deeper into any of these verticals I mentioned earlier. But you can also think about novel DeFi primitives. You have enough tools to really sort of like create novel things that couldn't be done before, and sort of really expand the horizon of what's possible in terms of a user experience in Web3. And to get started is pretty straightforward. You basically import a library directly. We have a specialized remix here that you can use to easily debug. One caveat, and this is also important to understand, is when you build confidential dApps, the biggest difference in the way you design dApps is thinking about information leakage. So what do I mean by information leakage? Information leakage is essentially when you unintentionally leak information because of some conditionals. So if you think about when you build conditionals in encrypted matter, there's no if-else statements, because depending on the path of execution, you can sort of guess, what the value is, right? So to overcome this challenge, there is something called CMUX, which is a multiplexer. And I'll use private voting as an example of how this works. So when you cast a private vote, this choice can be encrypted. And so it could be 0 or 1. So 0 for against and 1 for in favor. And then you can also cast a encrypted vote count. The first thing you'll do really is you check if the encrypted choice is equal to 1. And so what you get is an encrypted Boolean. So at this point, you don't know if the choice is true or false. What you do is you pass in this encrypted Boolean into a CMUX. So you can think of CMUX like a ternary function in JavaScript. So basically, if the value is true, it will return a truthy value. If the value is false, it will return a falsy value, which is the second argument. And so here in this case, when you pass in this equal, if the encrypted choice was true, it will return the encrypted vote count. If it's false, it will return 0, but 0 is also encrypted. So in favor count to cast here could either be the vote count or 0, but it's also still encrypted. You do the exact opposite for against, where the value that gets returned is 0, encrypted, if it's true, and then the encrypted vote count if it's false. So one of these two values would actually be the actual vote counts. And then you add both of these into their respective tallies. So one of them would actually increment. And so, if you were to build this in plain text, what it really means is you write if-else statements. If the choice in plain text is equal to 1, then add it here. If it's equal to 0, add it there, right? But like I said, that would actually leak information. So the way you want to write confidential dApps is really thinking about where can I possibly leak information. And thankfully, there are ways to write code to basically abstract away this challenge. In terms of decryptions, it's also important to understand what are you decrypting and who can see it. So essentially here we have two decryption functions. So one is the ability to decrypt the amount. So just to remind everyone, the way decryption works is there is a MPC network that basically collectively do partial decryptions, and you need a threshold of these partial decrypts to reconstruct the plain text. So a TFHE.decrypt here is when you want to decrypt a specific hidden amount, or a specific hidden value that you want to reveal to the entire blockchain network, but also basically entire world. So this is great for something like, let's say you want to reveal the final tally of a voting proposal, or maybe everyone's cards, for a poker game. So you use something like TFHE.decrypt. Re-encrypt is great if you want to query, let's say, your private balance, and only you can see it. The way this works is very similar to decrypt, but the difference here is that you actually provide the MPC decryption network a public key. So what happens is on the browser side, you generate a private and public key pair that's temporary. So you keep this private key on the browser side, and then you pass in this public key to the MPC network, which does the partial decryptions, but they will immediately re-encrypt these partially decrypted values into the public key you have provided. And so you get all these partial decrypts back to your browser, and only you can decrypt all these re-encrypted values and be able to view your own balance. So this is great. It's if you just want to view your own hidden values in a private manner without leaking information to everyone else. So this works for your balances, but also in the same example of poker, what if you just want to view your own hand? You use this re-encrypt function. So hopefully, I briefly touched upon this very briefly earlier. The way you encrypt data is on the client side. So once you encrypt this data, what you create is essentially this ciphertext. So this is where you basically pass in this ciphertext directly on chain and interact with the basically the blockchain system. So today we are able to support up to UN32. Down the line, we'll be able to support up to 128. There's also encrypted booleans and also other encrypted types such as bytes and also addresses down the line as well. So if you're interested in building, we are always happy to help you brainstorm. Really here to emphasize, we really believe this is the next frontier. There are just tons of novel experiences that you can build. Just to give you an example, when we basically participated in the ETH Global in Brussels, someone built a fully on-chain Risk game, which is a pretty famous board game. In Risk, there is some hidden information. You can only reveal the armies that are your neighbors. It's just a lot of these little novel experiences that I would say are quite unique, and we really encourage people to chat with us, and then we can help provide feedback and also help you refine your ideas. And lastly, we also have a list of novel ideas here that you can explore by scanning this QR code. It's a Notion page with additional ideas. And yeah, if you want to find more information about us, you can find our documentation here. We also have an arcade page where we showcase a few of these experiences. And yeah, definitely feel free to reach us out. And so this concludes my presentation.
Amazing. Thanks, Remy. That was such a cool overview of kind of how everything is going on at Inco and actual applications you can do with just these advantages in computing and kind of privacy. The question I have is, you kind of talked about largely the state of kind of how things evolved to where they are now, but I'd love for you to kind of actually give us an overview of like what's actually in the works and where is it going. So a super interesting part of what you're doing is that you are starting with only a few opcodes on EVM and kind of making them FHE compatible, and you kind of get to import that library and you have certain features in there. But what does kind of that evolution look like? Will this be 100% FHE EVM compatible VM that we're going to see in the future, or are we going to start with certain functions? Are there certain things that are in the works or easier to do? How does that actually become more practical over time?
Yeah, definitely. I would say the amount of operations that FHE supports today is probably covering 90% of what you already have in plain text Solidity. So like the additions, divisions, be able to do comparisons. The basics are already there. There are more fancy features that are in the works, such as shuffling. So imagine be able to shuffle over FHE, shuffle bits directly over ciphertext. That could come up later on. There's also the idea that we want to keep on supporting bigger types. So today we can do up to 128, which, roughly speaking, should cover pretty much most of the use cases today. Most of the ERC20s, even up to 64 is good enough from a typical Solidity perspective. But yeah, the idea is we want to support up to 256 down the line. The way typically the complexity for computation does increase as you get into bigger types, but obviously with hardware acceleration, things like this will become a lot more efficient over time as well. So I would say a lot of the features and also the way people should design dApps is very similar to how people already build on Ethereum, which is I need to think about gas optimization. I need to try to do as little steps as possible in terms of like compute and also storage. So nothing really changes, I would say, for most of the Solidity developers. That experience still applies for FHE.
Amazing. No, that makes a lot of sense. And kind of fundamentally what you're kind of saying is that as long as the basic operations are supported, you can kind of build everything on top, and you may kind of run into some cases where some specific cryptographic operations might be more expensive, but at least at a minimum, basic logic is fully there. And
there's a difference also. What happens with FHE is you're only using FHE for hidden state transition. So when you do a ZK EVM, you sort of have to build the entire circuit for the entire EVM execution, right? And with FHE, it's very different. You have the plain text execution, which is the majority of logic, but only the hidden state transition uses FHE. So in terms of scalability, I think a lot of misconception that people have is that, yes, FHE is known to be slow, but you also have to realize that FHE is only used at a specific touch point. And there is also the concept of block time in the blockchain space that actually gives you plenty of time to do FHE operation. So, yeah.
Oh, that's actually a very good distinction. Even Even I didn't realize that, even though like once you say it, makes total sense. Sweet. Well, thank you so much for this amazing talk, and hopefully people get to try out building practical applications with Inco on FHE. So thank you. And,
for this. Yeah, thank you. Thank you, Kartik.
And with this, we are ready for our next talk. And for this talk, I'd like to bring on Eunice to talk about how Mina is achieving decentralization by kind of building privacy and scalability and bundling all that really nicely well together. So without further ado, let's welcome Eunice.
Hello, thank you. Let me share my presentation then. Thank you very much, first of all, for having me today. Should I start directly or?
Please go ahead.
Oh, okay. Can you see my screen?
Yes.
Great, thank you. So hello everyone again. Today I'm going to talk about Mina protocol and how to design modular applications basically on Mina L1. So to have applications that can ensure privacy, scalability, and decentralization all at once. It's not something that we achieve at once, but it's just a design perspective, and I think I will be making much more sense till the end. So first, I will start with like where does Mina actually position itself in terms of this whole blockchain ecosystem. And then I'm going to talk about this conventional verifiable computation idea, which is today's main event, I guess. Then I'm going to specify what's Mina's approach actually in this computation models. And then detail to the role of knowledge proofs in Mina, both in infra and application sites. And finally, which is the biggest side, I'm going to talk about a specific use case, a censorship-resistant anonymous voting application. I think that's quite interesting because we'll be actually seeing a decentralized sequencing model on top of Mina, and first of all, how easy it is to actually be implemented, and second, how strong can it be? And we'll actually see that all this is possible due to the modular architecture. So yeah, let me start. First of all, in terms of positioning, I think we can actually divide blockchains or like blockchain contributions into three main big parts. First is like distributed payment systems. Of course, in Mina, we have an on-chain payment model to, first of all, have security in the settlement layer. It's the financial security, and also to allow on-chain L1 coin transfers. But I can easily say that that's not our main area of focus. That's not like what Mina is best at. And I think that's like true for a lot of blockchains. A lot of blockchains right now are focusing on this computational or storage sites, which brings to the second point, which is available data storage. Again, on Mina, we have a storage capacity and we provide liveness on our on-chain data, but it is quite limited, I would say. And we don't actually encourage our application developers to have their data stored on Mina chain. We actually push them to use external off-chain data sources, which brings power to Mina applications. Because when you think about regular Web2 applications, data and server is always separate. Like we never put them together, and that's something that we should keep. Thus, that was our approach in Mina, and we just focused on this verifiable computation power part. Mina is basically a big computer. It is a big distributed computer, and I can easily say it's world's first. You will understand much more when I like detail this sentence. I don't want to just say something and stay there. I will actually explain and show you why Mina is so strong in the computation power and so scalable in the long run. So I think in order to understand what Mina does differently, we need to see first like how conventional blockchains work. So I believe this model is true for like almost all blockchains, at least for the ones that are like compatible with Ethereum. Some tweak this a bit for privacy purposes, but in the end, always validators are positioned in somewhat similar manner. So basically here, let's define our on-chain state updates as a function. So, all state updates can be a function because in the end, we are inside a computer, like a state machine. So this can actually be, something that is mapping input to output. And we can think of all these smart contracts, Solidity or something else as functions. And in regular blockchains, this can be Ethereum or something else. Of course, like a blockchain that allows computation on itself. User sends the ID of the function and the input to the validators. This ID, I mean like the smart contract public key, and of course the name of the method. So basically you say that I want to call this smart contract and this specific method. And then you also send your inputs. As you know, in blockchains, in regular blockchains, all inputs are public, just because of Mina. So they're public, and we should send our inputs to the validator set. That can be either through an RPC in like live layers through a light node or light client, or other possibilities. You can have your own full node. It does not really change. You need to gossip the input to all validators in some way. And then each and every validator, they just compute the F function from scratch. They get the input, they run the F, and they like compute the output, which is the state change. So you can be adding something to a mapping. You can't be changing some Boolean state. It does not really matter again, but you are creating an output. And we want our validators to be actually on the same page in terms of this correctness of the output, so that the computation itself is verifiable. If we don't actually make all validators do this computation, we cannot be sure of the correctness of the computation. And if validators do not do, each of them, the computation, then they would be trusting on other validators, which is a problem. So they just repeat the computation, and then they gossip the output. They put a consensus around the output. Here, the ordering also matters for some outputs, not important. But in the end, they come to the same conclusion of the state update. And then they update the state. So I think that model is quite known by blockchain developers. You would be like, why he's repeating all that? Because I think there are a few problems that we don't actually think too much about in this very standard model. In terms of advantages, it's quite, I guess, clear. First of all, it's trustless, this entire setup, because we assume that the validator set is decentralized, but that's a world assumption, like below all blockchains. Thus, it's verifiable also. User can verify the computation, validators can verify the computation, so there is no trust in any party, and it is deterministic. So this function actually be setting itself to not being able to be updated, meaning that maybe even the smart contract developer be unable to deploy or redeploy this function, without asking the consensus, without asking their users. So that's also really an advantage of the system. In regular Web2 architectures, you can just change the backend and no one would ever know. But in blockchain applications, you can even set the function, set the application to not being able to change. But here there are two problems. First of all, there's no privacy. So I think the presentation before me, it was on pleomorphic encryption. So yes, of course, there are cryptographic solutions based on application that can give you some privacy. But first of all, this does not change the fact that the input itself should reach the blockchain at some level. And the second, these cryptographic manners, they do not always apply. I think that's an important observation to do. In the end, there is no end-to-end private connection in this setup. Like entire computation happens before everyone. So that actually kills the privacy. So even your input is encrypted, people can, learn different stuff from their inputs, or like some applications cannot use this setup, etc., etc. So that's the first issue. And the second issue, which is, I think, much more hidden to regular talks, is the fact that this application is just do not scale. Like this architectural model, this will never scale. Because first of all, it is repeated. You can have as much validators as you like. You can make a system much bigger, and this would just make the system slower. Because as there are more validators, then the consensus is just much slower to finalize, so that the state update, the block time is higher, which is a problem. And as there are more and more users, this is again the same problem. Like there are more people using the system, so the system just slows down. This is a fine architecture in Web2 models, because in Web2, if you have more users, you can just use some of your earnings to scale your server, so that your server can actually handle more requests. But this basic setup wouldn't work with decentralized systems, Because validators, they do not make that amount of money. If you really want very big servers, then you should be really strong, really powerful to actually be able to get these machines, run these machines. And at some point, like if the entire internet was on a blockchain, this model would actually end up by having like all validators being either Facebook or Google or like, these big service providers. So that's quite an issue. So when we think hard about this system is never designed for hard computation. It can be scaled like through rollups, etc., etc. But we all know that rollups bring their own issues. So Mina asked this question: that is this the best model? Like, can we do better? So we have a different approach. Again, the problem is the same. We have this function f, which is the same function. It really does not matter. It has the inputs, it has the outputs. We want to update the state based on the update. So first, in Mina, we have the user here, by the way. Sorry, this was from a Turkish slide, so that's Turkish. I just missed. So the user computes f with the input, and it generates this knowledge proof. So the computation itself does not happen on validators. The computation happens on the user. So I will come to the implications of this. But before that, just grasp the idea. The validators, they don't do any computation. To be honest, in Mina, validators, they even don't have the smart contract. The smart contracts are entirely lived and computed off-chain on the client. The blockchain has no idea of the computation itself. And then you just send the output. You just say to validators, I want to set the state. But like, just easy as that? No, of course. You also send a zero-knowledge proof. So each Mina validator, instead of redoing the computation, they do the zero-knowledge verification. They just verify the proof, check it to be the correct output, and update the state. Here, if you are like a bit technical in the zero-knowledge architecture, you would be asking like, how can I know it's the same proof? So basically, we use verification keys there. It is again a constant-sized key. So developers, they just deploy their verification key instead of their smart contract. So basically, this zero-knowledge proof is run against this verification key to actually, check correctness of the proof. Just being able to verify, but also being able to verify the correct stuff. So that's Mina's model. But what does change in this model? First of all, in Mina, we use ZK snark proofs, which are zero-knowledge proofs, and they do have zero-knowledge property. So there's privacy. Not by default, not by anything. It is the only choice. Like in this setup, it's actually impossible to gossip your input to the validators without, choosing it. You can, of course, like choose to send your input as it is to the validators. But besides that, the computation does not reveal the input at all because everything happens inside the zero-knowledge proof. So there's 100% privacy here. Without needing any other cryptographic technique than the zero-knowledge proof, you actually allow your developers to like have limitless amount of privacy. This is the ultimate privacy you can get because the input never leaves user's computer. The second is another property of ZK snark proofs is the constant verification time. So ZK snark proofs are the special type of zero-knowledge proof that are always verified in the same time, the constant time. So you can have like as many inputs as you wish. The computation can get as complex as it can get. The verification happens always at the same time. So basically, the gas that you use in a computation, in a smart contract, does not depend on the computation itself. So you can have a very simple smart contract that does like counter, or you can have this amazing AI smart contract that does on-chain AI. Both consume the same gas in Mina because the verification is constant. It just depends on the network overload. If there is high overload in network, then you can pay a bit more gas or a bit less, but there is no relation between the computation and the gas fees. So that's also quite impressive when you think about, because what do we want from computation? Being constant is the perfect way to scale our computation. And the final is a bit trickier. It's the aggregation side. But I will explain this from a real-life use case, which is Mina itself. So I can talk about a lot of different applications on Mina, and today I will talk about one. But honestly, if I were to talk or explain everything that's possible on Mina, that would take like hours and hours, because with Mina's architecture, You can basically model anything in a scalable manner. But I think the blockchain itself is a great example. First of all, we have privacy in Mina, like the entire network is private. Because the entire Mina blockchain is a zero knowledge proof. It's actually, like we always say Mina as a blockchain, but it is more accurate to describe Mina as a zero knowledge proof settlement and also aggregation layer. It is this big zero knowledge proof that like can include other zero knowledge proofs through aggregation, and always stays in the same verification time. The aggregation is, recursively including other proofs inside another. And if you get ZK snark proofs wrapped around other ZK snark proofs in a recursive manner, like think of images of images of images, you always take an image, showing the other image, you actually do aggregation. And since, as we said, verification time is always constant in snark proofs, the entire Mina block history can be verified in constant time. It's not logarithmic, it's not based on a tree or anything. It's always constant. You can have as many blocks, as many history in Mina blockchain. It's always verified in the constant time. And the final, which is I think much more impressive, is the size. We always say that like snark proofs are verified in constant time, snark proofs are constant size, they don't depend on input. That is true, but partially. You can actually use snark proofs in a constant sized manner. If you aggregate ZK snark proofs, count of aggregation does not change size of the ZK snark proof. If you have this, constant 20 kilobyte size after the first recursion, then that just stays the same. You can have as many blocks wrapped around each other as a zero knowledge proof. The size stays the same, which in the end allow Mina to be 22 kilobytes. The entire blockchain history is 22 kilobytes, which is the ultimate verifiable computation. Because in most of other verifiable computation environments, you are just able to verify recent history. Of course, like you can go from Genesis, you can sync, but first that will take hours. And second, there is no availability guarantee because that's not the idea. Like they are not based on that. You really need a lot of liveness. You need to be able to like reach all this consensus, all these blocks to be able to sync from scratch. But in Mina, that's not the case. It is a ZK snark proof. It is of constant size. And validators, they only have the final state, but still they are able to verify the entire block history. They don't have final 10 blocks. They don't have final 20 blocks. They don't go to the last fork. They can just have the final state. But since it's 22 kilobytes, it can also be included, the entire blockchain history, in a single validator. It is basically, a WhatsApp message that you send. You can send the entire Mina blockchain in WhatsApp to someone because like it is so small. And like I think that's an excellent use case because this is not an example. This is not like a theory or white paper. Mina, I think it's on mainnet using the same ZK infra for like 6-7 years, much before my time. And it is still 20 kilobytes. There are like $1 million on it, and there was never a breach. So we can see how strong ZK snark proofs just by examining Mina. Of course, the blockchain is sometimes like clashing and like there are errors, but in that there was nothing that actually made us question snark proofs capabilities. It was always there, it was always a constant, and it was always verified. So there's no need to trust, or there's no need to sync. So that was all from the theoretical side. And for the last bit, let me talk about a use case, which is, I think, quite interesting. So the first bit of anonymous vaulting, I think that's quite known now, or it should be. So basically, that's what we always try to do with privacy applications. If you can do a voting application anonymous, then you can do a lot. But making a voting truly censorship resistant is quite a challenge. And how we can achieve that in a scalable manner, that's quite a hard question. And here I have this small setup where I will explain how easy to actually do this in Mina. So let me start from this bottom bit, which is user. In Mina, user is a part of the network. Since we actually don't have any computation power on validators, but they just verify, the computation power is actually user itself. So every user joining the Mina network it actually brings its own computation power. Thus, at the beginning of the slides, I said that Mina is the first distributed computer. It is not the first decentralized computer. Ethereum is a decentralized computer. There is trustless computation, but Ethereum is not distributed. The computation is just repeated among validators. But in Mina, it's truly distributed among every participant. Every participant just joins and brings its own computation power. So first, it starts from user level. We have this initial set of public keys that we want them to vote. So we basically say that we have this 200 people that will vote. There can be 100 votes. Maybe half of them didn't vote. That's okay. But in either case, we don't want to know who voted who. Like we should not be able to see if someone voted, and if they voted, we should not be able to see who. Like we should not be able to see anything about the user. But we should be sure that the vote is coming from the same set. That's the important point. So first, the user creates a knowledge proof. So I won't give too much detail of the proof. It's actually quite easy to code in Mina. It's like 5 lines of code. I can literally send it. If you're interested, that just DM me. So the proof itself, it gets the private key of the user as private input, and the Merkle witness. So we can get private key as an input because it's a private input, so it's never revealed. And the public input is the Merkle root of voters. Here, the Merkle tree is a structure that we use commonly in Mina. Maybe it is less known for Ethereum developers. It's quite an easy. It's an hash binary tree, basically. It is used a lot in verification. And everyone doing heavy verification, they use it, like in Web 2 as well. Not something very new. But if you don't know it before, just check it out. So we just sent these to actually verify the private key to be included in the set. And basically, once we have this small proof, which is a few kilobytes of size, we can actually prove that the user is inside the set because the private key and the Merkle witness can actually verify the private key to be in the Merkle root, but they don't say who in the Merkle list. And also you get the vote as the public input and you give the vote as public output. If you want to make a bulletproof vote, again, a voting concept, you can use fully unmarked encryption. But just to make it, a bit different, the voting setup, it does not make more anonymous. It just, makes it a bit more private. So that's setup. And the CK proof is amazing. But there is this small problem that allows double voting. So basically, the voter can use this proof to vote multiple times because it's private. I always say, if something is really private and really decentralized, it's really hard to, make money or, censor something because, you can't actually say someone that you use this because, it's private. So it's really hard to actually, monetize. So it's the same concept. You can't actually understand if the user voted before or not. But there's a small solution, very easy solution. We just add a nullifier concept. So nullifier is just a cool word for an identifier that is anonymous. Basically, we also output hash of the private key. So since this is knowledge proof, we can do any computation trustlessly inside as we want. So if we say we get the hash of the private key, then that's the hash of the private key. Everyone knows. But since it's the hash, no one can track the private key back from the hash. But if I try creating a knowledge proof using the same private key, then I would actually be outputting the same nullifier, which is an error. So, everyone can detect that, okay, these two votes are coming from the same person. So the problem is solved. That's a nullifier. Just a small detail, by the way. If you are I don't know, if you're wondering, the nullifier should also include a global ID of the election so that there is no pseudo-anonymity between different elections, but that's quite a detail, so I just skip. So once I have the vote itself is private, I need to aggregate them. So I need to actually count the votes, get a final result by adding up candidates, and settle it somewhere. But first, I need a communication layer. So the user just sends it on a DA layer. Here I have DA layers, which is not an error, unlike before. You can actually use multiple DA layers at the same time. But before coming there, let's think of a simple DA, like Celestia Avail, something. The user gets its own light node in its device and sends the knowledge proof, a vote, to the DA layer. So right now, anyone can actually see the vote. They cannot understand who has sent this. There's nothing that like identifies, but there's a nullifier, so they can check if this vote existed before or not. So that's like amazing for anyone that want to count. Here, since we use light nodes, there is no censorship risk in terms of censoring the user before reaching the communication layer. Here, DA is not a storage, it's a communication. We just need votes till we finish counting through sequencers, which I will come in like a second. But that's important because normally DAs do not give us personal storage guarantees. Thus, we just use them for communication. I just set my vote there and wait to be counted. So then a sequencer reads me, aggregates me, gets proofs together, and settles to Mina. But there's this small error. Sequencer can just ignore me. So if I have only one sequencer, which is like almost always the case with rollups, then the rollup can just ignore me, can just choose to not see my vote. I can use, of course, a homework encryption solution to actually hide my vote, but there are like still censorship parameters. I can censor my user based on the location. I can censor it based on like time, etc., etc. So none of these cryptographic solutions is actually a solution. We need the sequencer to be decentralized, but that's actually quite easy to fix. Instead of saying Mina, allow this public key to sequence and then to settle to me, we just say, okay, Mina, accept anyone you like, but choose the one with most of the votes. So if the sequencer is sending a proof with 10 votes, and this is sending with 9 votes, then you accept the one with 10 votes. There can be 12 votes in reality, like 11 votes. But if this is sending 10, then that should be more correct. Because since there is zero-knowledge proof aggregation here, no sequencers can lie. If they say that there are 10 votes, then they should be able to reach 10 votes. They cannot get 10 votes by aggregating 9 votes, so that's impossible. And by just having this simple maximum test in Mina, which is just an easy assertion, so that's one line of code, you can actually say that anyone can sequence, but I will accept the one with the highest number. So if there is only one honest sequencing network, if there's only one honest person to aggregate these votes, that is done. You can settle in Mina and you can get the correct results. And two small details here. First of all, like people can say your aggregation is not possible, so this sequencer should be really strong. This is not true because we have Mina. So Mina aggregates the entire block in like seconds. So it's quite easy to aggregate these blocks, even with a personal computer. So these sequencers can be really light machines, which just increases the decentralization. And the second is the previous point that I made. This DA layer can be of multiple. Like you can actually sequence multiple DA layers at the same time because Mina does not depend on DAs at all. Like there's no connection between the two. So there can be like 3 different DAs here. And user can choose one of them to send this vote. And then the sequencer can track all of them and get all these valid votes and sequence them in the same ZK proof. That's also quite an easy fix. So that's also a very well scalable solution. And I think that's an excellent use case to actually show Mina's power. Here, the application is private. It is scalable in many different manners. Like we have different sequencers, we have different DAs at the same time. So it is very scalable. And it is really centralized. The entire blockchain history is provable. So that's the best settlement layer possible. The sequencers are decentralized. Anyone can sequence. DAs are decentralized. There is no trust in one DA. Like you can even change DAs, and the computation just happens on the other side. So I hope this example was helpful to you. These are my contacts. This is wrong. Sorry, both are wrong. It was correct in the first slide. So these are my contacts. Please feel free to reach anytime you like and ask about your questions. It's not only for hackathon, but on Mina we have different grant programs. So if you want to build something that can truly scale, just reach us and talk to me. I would be happy to help for your architecture. Even without Mina, I'm always eager to discuss blockchain. So thank you, everyone.
Amazing. Eunice, thank you so much. I think it was very helpful to actually see the part you focused on at the end, which was actually walking through the whole flow of what a transaction looks like from the user side to confirmation to just kind of where all these new schemes come in. So really appreciate that. I think the only kind of question I want to ask and end with is, what exactly is the surface area for like what you can actually improve from here? It's amazing that you have a constant size blockchain. It's amazing that you have these guarantees on kind of the information being compressed is going to be correct. But does that mean we're done? Does that mean things can't be made better or faster? What do you kind of do from here on, and what exactly is the improvements that will be possible as kind of we see this whole field itself improve on applied cryptography? Oh, I think we.
Great question. So yes. Yeah. So there are a lot of areas to improve. No, we are not done, not at all. I go from the order of importance. First, it's quite complex right now. I know this architecture is complex, and like it can be a bit fearful for newcomers. So first of all, we should abstract more. The client-side package should be much easier to use so that you can access these different layers without even noticing. And we are quite close there because O1.js, Mina's framework language, it is already on NPM. So we can just have other packages included inside it. So that like there is this nice wrapper that you can easily use in client side. I think that's the first thing to do. Second, there is this concurrency issue. Since the entire Mina blockchain is zero knowledge proof, and it is totally verifiable, there's an issue about reaching to the smart contract, which should be solved with a common aggregation layer, available aggregation layer that Mina should include on itself. It exists right now, but it is not working quite great. We are right now working on fixing it. So once it is fixed, it will be much easier to deploy applications on top of Mina without using other layers. So right now, you really need other layers to make something that's like good scales in a good, like fast manner, I would say. So if we had this aggregation layer on top of Mina natively, that would be a good fix. And second, right now, block time is not really fast. It's not quite important because that's a rollup layer, like that's a settlement layer. So every application on top of Mina, it's already a rollup, even if you don't like notice. So it's not really important, the settlement time, but still like a smaller block time, meaning a higher TPS, would be a good change. And right now we are working on it. I think in about 4 to 6 months, there would be a big update that will like dramatically improve this performance. And yeah, so these are changes we're working on in general. And yeah, thank you for the question.
No, that's a pretty long list of things that are just actually very incredible and performant improvements. So it's not a small thing. It's going to take a lot of time and testing and perfection, but this is great. I think that's everything we have for today. So I want to thank you again for preparing this amazing presentation and kind of really helping all of us visually understand how this works, which is, I think, going to be very useful to give to others as a video next time for them to follow. So thank you. And with this, I want to say that this was officially our last talk for this summit. This has been the Verifiable Computing Summit. We wanted to actually show you the potential of all the new cryptography improvements that we're seeing in this space. And a lot of this is something that you get to actually use and try out and play with and include that in your hackathon project. So you have 10 more days left to go before the hackathon submissions are done. So I want to wish everybody happy hacking. And with this, we'll see you all next Friday with our Scalability Summit. And in the meantime, enjoy some lo-fi beats, and we'll see you all on Discord. Take care, everybody. Goodbye.